Alright, back to threads, multi-threading with C++, and today we're gonna advance to WinAPI threads. I could go several routes here. I could completely delete everything that is in here, but I don't want to do this. I'm gonna create a new file. I'm gonna call this winmain. Well, actually, I should call this winmain, because it is a white winmain, because white winmain is king. And then we're just gonna do everything again. Windows.h, so int win API win main. I'm gonna get some parameters soon. I'm gonna quickly return. I mean, there is kind of like a constant that is returning valid, but I'm not gonna use this. Alright, so we're gonna have an h-ins. What the fuck? There we go. So h-instance, so we have the h-instance here, which is just like your default Windows arguments. pv string in CM command line arguments, and then we're gonna have an int command show. Alright, this is like the signature for WinMain, but the thing is, this is not gonna be used. We need to wrangle a bit on my configurations. Okay, so I need to do some solution configurations. I would actually like to create another platform for Windows and normal x64, but this doesn't work. So I need to do new configurations. Alright, so we're gonna have another debug configuration, and we're gonna call this debug WinAPI. Alright. We're gonna create a new one here as well. Now we're gonna copy this from release, and we're gonna call this release WinAPI. So we're gonna have a version for Windows, and we have a version for normal C++. Now, of course, I need to do some more configurations. So let me first select multiple configurations. I wanna just have the WinAPI configurations, and in the link I'm gonna go to system, and I'm gonna change this from console to Windows, and this should actually do the trick and invoke WinAPI as soon as I select WinAPI. Let's test this. Let's just do a message box here. Alright. So just like that, just to see that something working. So let's start by the normal debug configuration. Let's just go to debug and see what it's doing. It shall invoke the other main. Let's see. Yeah, it's like invoking our normal main that we were using like the last videos. Now let's switch this to debug WinAPI, and this should now invoke the message box. Yeah, there we go. Now everything is good. We have another configuration up and running, and we are now able to select WinAPI, so Windows threads and STD threads. So let's take actually a look at the documentation from Microsoft, because well, it's like not that easy to do threads on Windows. It's a bit more different. You have actually this create thread function, and we're gonna try out how this works. We're gonna just create one thread here, so we're gonna have a handle for that thread. So in Windows we have a handle, so the h thread is the handle to the thread. It's just like so many things in Windows are handles. And we need attributes, a stack size, a start address, a parameter, a creation flag, and a thread ID. Alright, so let's actually go through them. So first, the thread attributes. We actually don't need them. Security attributes by default. If you're not doing some advanced stuff, you can like always put this to null. Now the stack size. The stack size is the size of the stack of the thread, so you can actually have different sizes of the stack, but in this case we're not going to use it, or we want to use the default one, so we can input 0. Then we need a start address. The start address is a LP thread start routine, and this is basically a function pointer to a thread proc, and this is the signature of the thread proc. So let's actually copy the signature here and create this up here. So there we go. This is like the thread proc. I'm gonna rename this to thread main. Actually, Let's do this like that, so that we are in line with that. Yeah. Alright. Actually, we're gonna alter this in a few seconds. So, I'm gonna call this here thread main. So this is gonna be our thread function, and by default it's just gonna return 0. Alright. So we wanna actually put in a function pointer to that function. There we go. Then we need some parameters, and actually the parameters, you can say that this is an LP void, LP parameters, and this thread main also have this parameters LP void in here. This is just passed to the thread, so we could do a struct here, thread, or just call this thread args for thread arguments, and I'm gonna pass in some arguments, so we're gonna create, so this is actually creating the thread, and I wanna actually create the arguments here, create thread args. So we're gonna have some arguments here and we're gonna fill them in. Maybe for starters, let's do an std. Okay, and of course need to also include this. So let's include this. Let's include string here. Gonna std string here, and this is like the message that is gonna be passed to the thread. So I'm gonna say args port message is hello. Or actually, let's do white string here. Gonna say hello. I'm message for the thread, and I'm gonna pass this args into here by passing the pointer in there. Then we have some more. Actually, did I forgot? Yeah. Yeah. Then we have this thread start address, and then we have our parameters. We have creation flags and a thread ID pointer. The creation flags are actually quite interesting. So first of all, if you don't put them in, the thread automatically starts no arguments. You have this create suspended, which basically creates this thread, but the thread is not gonna start. So the thread is not gonna be executed. We're actually gonna use this to actually show you what the beauty is with WinAPI threads. Actually, this is like the most beautiful thing that WinAPI threads give you, this create suspended. Not that, nah, actually they have more, but it's quite good. Alright. Yeah. Alright, so basically you can actually specify with the second argument if the stack size is a reservation or if it is a committed size. So by default it will automatically commit the memory, so it will allocate the memory for that thread, and the thread has all the memory available. If you don't have this, it is just like reserved. You actually just reserve this size, but you are not actually committing this to memory. You will probably not use this, at least if you start with that. Then we have the thread ID pointer. So basically on Windows each thread has an ID. So the ID is a dword. So we have this thread ID, which will start at 0 because like invalid. And in this argument I'm gonna also pass in a pointer to the thread ID, and what it will do basically is it will set this thread ID to the ID of that thread that was created. So this variable is set to the actual ID of the thread, of this handle thread. So I'm gonna check if this is invalid is not invalid handle value, because if it is an invalid value, that is bad, because, well, the handle needs to be successfully created. So I'm gonna check if this is invalid to invalid handle. It is probably... No, actually the value is null. It's like a bit different. Some functions on Windows return on failure invalid handle value. And some functions return null in the case of an issue. Okay, I have some lags here, sorry. Alright, back here. So basically this is I need to check if this is not null, or actually I could say just if h thread, which would be a bit, yeah, easier to do, and then I can basically do something. So basically this will create a thread, but it will not dispatch the thread. But let's actually alter this a bit. So actually we're gonna change this to that, which will break compatibility with that, but I can easily cast this to a LP thread start routine, and everything will be good again. This just makes things a bit more easier in our main for that thread. Alright, what I'm just gonna do in this thread main, I'm just gonna display a message box with our arguments message cstring, and gonna call this here thread. thread, and actually let's do some more advanced stuff. So let's just make this MB OK and MB icon information. Let's actually show you what the beauty is of creating that thread suspended. So let's add actually a divert here. Thread ID. And let's actually display message box here. And what we're gonna do here as well is we are gonna use a string stream. So let me actually include as a stream here. So we're gonna have an std string stream vss, and I'm gonna import here thread ID, yeah, and let's do args thread ID. And let's actually use the VSS here, string C string, there we go. And yeah, now we need to, of course, populate the thread ID, which shall only be populated when the thread is valid. But the thing is, we are creating our thread suspended, so we can easily alter the start arguments because they are just a pointer, and the pointer will not be altered, but kind of like the target data of that pointer will be altered here. So we're gonna actually pass on the thread ID. So we're gonna pass on the thread ID to the arguments struct that is created here, and the thread will obtain a pointer to there, and as soon as we start the thread, it will see the valid thread ID even though we have assigned the thread ID to the arguments after the thread has been created, which means, or in normal C++ would mean that the thread may already have finished execution, which would be bad in this case. Of course, I could like get the thread ID. I mean, get thread ID. Okay, this needs a handle get current thread ID. So I could like use this function here because we will do essentially the same thing here on Windows. But yeah, I'm gonna use this there so I can like this so that I can show you the beauty. All right. So of course we need to destroy our thread at some point. So destroy thread, and destroying a thread is just done by closing the handle of the H thread, which is yeah, we're gonna just do this like that. This may arise in an issue now or later, but let this keep like that and start it. And what you can see is nothing. Why is that? Because, well, we have closed our handle. Actually, this is gonna be an issue as soon as we do start the thread. So basically what we have done, we have created a thread and we have directly deleted the thread. It was never running. So we need at some point run the thread. And we can do this by calling the resume thread function, which will basically resume the execution of a thread. And I'm going to input my thread handle here. Let's actually take a look at this function. What arguments does this has? Let's say... what is the return value? The function fails and the return value is -1. Alright, so -1 means this is invalid, so I could like say if this is equal to -1, then I could like say, let's actually do this here, let's just return -1 here as well, so just like that. Alright, let's try this out now after we started our thread, and yeah, nothing. This is an issue. You can like see, even though our thread is now running, we get no message box. Why is that? This is of course because we are directly closing our thread, and you can actually see down here, or where is it? Why did I have an invalid code now? Okay, it may depends on how fast the application is running, but actually it seems like our thread has been aborted. Alright. So let's actually do something. After we run our thread, we need to wait for the thread, and you can wait for a thread by calling the wait for single object function. We're gonna wait for our thread, and we're gonna wait infinite for our thread. So basically, this will wait until our thread has finished execution. So let's try this out. Alright, we get our message box. Hello, I'm a message from the thread. And I can press OK, and our application terminates. Let's actually trace this down. Let's actually do some breakpoints in here. So let's do a breakpoint here, and let's do a breakpoint here. Maybe also do a breakpoint there to actually tell you what's going on here, and maybe there. Alright, so let's start the application. First of all, we're going to get a breakpoint here. Can see that our thread arguments are populated. You see the message is hello, I'm a message from the thread, and the thread ID is 2400. And as you can see, the thread handle is also a valid value, so everything looks good. Alright, the next thing is we're gonna resume our thread. And the next breakpoint is this wait for single object. So basically, this is waiting for our thread. We could now actually take a look at where the other thread is currently at execution. If we take a look at here at the thread drop down in Visual Studio, you see this main thread, you see the NTDLL thread, and you see this multi-thread tutorial exe thread main, which is basically our other thread. And you can actually see that this is currently at NTDLL PDB, so it's actually like not not on a point of interest currently, but you can also see in the call stack that this thread has not reached a point where we can trace it down. It's still like on its Windows creational stuff currently. So right, let's switch back to our main thread and let's continue on. And now you can see that we are into our thread, and you can also see that our thread stack has changed to the multi-thread tutorial access thread. And you can also see that we have our arguments in there with our messages and our thread ID and our correctly crafted white string stream. We could switch to our main thread here, and you can also like see that this is currently in wait for single object, because the next thing that would be executed is this close handle. So we are currently like in this external frame from wait for single object. So basically we are currently in Windows code for wait for single object. And you can see as soon as I continue execution here, we get our message box, and I can press OK to close it up, and we are now at our close handle back again, which will close up our Windows handle for this thread and will properly finish the execution. Alright, now let's actually tweak this a bit and show you the beauty of WinAPI threads. I've removed all breakpoints. Now let's imagine you open up this message box, and this message box needs to be, okay, I mean there's just an OK box, but there could be a yes and no action that you can perform. And you may actually want to just have this option available for like 10 seconds, for example, because after 10 seconds it is no longer valid to answer this message box, because if you're not, because this may actually be some action that needs to be done very quickly. So something like system's gonna shut down in 20 minutes, in 10 seconds, so you wanna abort, yes, no. If you press no, it will directly shut down the system, or in this case the application, and if you press yes, it may abort, for example. And after these 10 seconds you wanna automatically close this message box. And this is actually you can actually do this by using Windows API. We just need to alter this wait for single object. First of all, this is like the wait time in milliseconds. Let's go for 10 seconds. It should be sufficient. 1, 2, 3. So this wait for single object will now take a maximum time of 10 seconds. After 10 seconds, it will actually terminate. So to actually catch this behavior, we need to check if this is not invalid to wait object 0. Wait object 0 means the wait succeeded, or we could actually do this a bit more differently. We could actually take a look at if this wait has timed out. So if this timeout value has been reached. So as soon as this timeout value has been reached, I'm gonna just do another message box here, and I'm gonna say MB okay, MB icon error, and I just say error message box not closed within 10 seconds. Alright. But before we're gonna display this message box, so we're gonna display message box, we need to abort thread. Abort other thread. Let's see if I have this function in mind. So abort thread or destroy thread. Alright, okay, no, I need to take a look at this function. Thread, okay, it's actually it's terminate thread, and you can force terminate a WinAPI thread here. So I'm gonna say terminate thread, and I'm gonna say h thread, and I'm gonna exit code the thread with -1. This will actually be catched by the Windows compiler with an issue here. Because using terminate thread does not allow proper thread cleanup. Yes, I know, but this is not like 100% clean what we are doing here, but I just want to show you that you have the the ability to do this here. I could actually like ignore this warning. This is like I could ignore this, but I'm not gonna ignore this here. I'm just gonna leave this like that. So yeah, actually we could let's just do this here first. So alright, we're gonna start this application now, and we're gonna have this message. I'm gonna press OK. Everything is going to plan. Our threads all returned with exit code 0. Let's now start and wait until the time elapses. So I'm just gonna wait a few seconds there. Maybe 5 seconds would be more sufficient, because 10 seconds are still a bit long. And you see that the message box has disappeared, and we got another message box which obviously didn't show up, but yeah, it's okay. And this message box says message box not closed within 10 seconds, which is exactly what we had. And the other message box disappeared because this terminate thread actually does clean up a bit. And you can actually see that there was a thread terminated with an exit code that was not 0. So here you can see the thread 0x7b2c has exited with code whatever, and this code is equal to 0xffff, which is basically the value of -1. So you can actually see that we have a different exit code, and we actually want to catch this exit code. Get thread, I think, is it exit code? So we want to have the function get exit code thread to get the exit code for the thread, and I'm going to input my thread handle, and I need a divert, which is my exit code, which is by default 0, and I need to input this exit code here as well. And then I can make a little message box. So actually, like, I could say if this succeeds, I'm gonna make a message box, thread exit message box, and I'm gonna create another white string stream here. I'm gonna say thread finished with code 0x, oh actually, yeah, let's do a hex. std hex 0x exit code, there we go. Let's say a simple darn message box with no window, white string stream, string c string, finish, and this is gonna be finish. I'm gonna say mb OK, mb icon information here again. Alright, this we're just gonna catch the exit code of the thread again. So let's actually start this again and see how this was working. So I'm gonna click this directly, and I'm gonna get another message box, thread finished with code 0x0, which means okay. Now let's start this again and just let's actually stop this and actually reduce this time to 3 seconds. This is gonna be sufficient. I don't want to wait that much time. Yeah, 1, 2, 3, go. And now we're gonna get this message box. Not closed within 3 seconds, because this was catched here. And then we get another message box, thread finished with code 0xFFF, which is basically the code that we have forced here with this terminate thread. Alright, so this is all working. So you can see like that the WinAPI threads are much more capable. Now I'm gonna actually show you a bit more how window threads work, and for them I need to actually increase this time again to actually show you that a bit more easier. And the thing what we are gonna do is thread affinity. So binding one thread to one core. And to actually show you that, I'm just gonna do some pointless work. Do pointless work while true. Alright, so just an infinite loop in our thread. This will just result in an application not showing anything, and it will just, yeah, crunch some numbers, and at some point we're gonna get the other message box that, yeah, we didn't close the message box within the time. And yeah, this is how it is. Now let's open up the Task Manager Deluxe, which is free for educational purposes like this video, or also private use. It is like a better task manager which can show you, oh my god, didn't I change this on this system to the dark mode? Preferences, visual, dark mode. There we go. Nobody likes bright applications. Let's just put this side aside. And let's go to system. No, performance is the right window. And this is actually showing you the work of each single core of your CPU. So each of these boxes represent one core. And if I start my application, you will see that one core is gonna spike to a maximum. Yeah, there you can see like this core is now at a maximum usage, and this is the core where the while loop is currently running on. And as soon as the while loop is finishing, you can see like that this peak is going down again. So you saw that this was this core CPU 27. So this core did the work. Now let's try this out again and see which core is now getting the work. Alright, it's getting the same core again. It's a bit unfortunate that it is getting the same core again. This is probably because of some Windows scheduling. I don't know why it is kind of like assigning that to my thing. Let's try if we get another core. Yeah, now we get another core. Now we get core 25. So you can see that every time we run our application, we get a different core that is running our application. So basically, create thread by default does not specify which core is gonna process this. So it's not defined. So it's getting any core that is available. But we may want to do a job system on our engine or on our system that we are programming. And a job system basically means create a thread per core or nearly per core. Or maybe if you have like 8 cores and you have like hyper-threading, then you have 16 threads available here. And you then, for example, just take 8. Or you make this user definable so the user can select how many cores you want to use by the job system. And what you basically want is you want to have one thread per core, basically. And to do this, we need to tell Windows which core this thread is going to use. So this can easily be done by setting a thread affinity before we resume it, before we start it. So for this action, it is very important that you start this thread suspended, so that you pass this create suspended flag, because if you're not starting this suspended, you are not like setting the affinity in time. So just if you then would pause the thread and resume it, then you would basically set the affinity there. So we're gonna set the core for the thread, and this is done by set thread affinity mask, and basically this is a mask. So basically you can actually enable which cores are allowed to run on. Okay, this is a pointer, a dword pointer. So we're gonna have a mask here, which will be 0 at the starter, at the beginning, and we're gonna input this mask here. Why are it not working? This is a dword pointer. Ah, okay, I know what's the issue. Dword pointer just means 64-bit mask, sorry. I did a misassumption here. Dword pointer is basically a 64-bit value, which basically each bit stands for one core. And basically if you have more than 32 cores with hyper-threading, so basically a big thread ripper, which has 64 threads, then you're gonna need to do this a bit differently. But yeah, basically you're not gonna use more than 64 threads, so you're actually good with taking this normal dword pointer mask. Basically, what this mask is controlling is basically this is binary, and I could like do 64 zeros here, and basically each of these zeros represents, or each of these bits represent one thread, one of these boxes here basically. And by setting a 1 at 1 bit, this tells Windows this thread, this core, is allowed to execute this thread. And for that we are actually gonna use some bit shifting. So I'm gonna take 1 unsigned long, and I'm gonna shift this by 0. And basically what this means, enabling, or actually let's do an unsigned in thread index, which will start at 0, and let's just shift this by thread index. So basically what this operation does, it's just setting that bit that is defined by thread index. So in case I have this at 0, it's just setting the 0th bit. If I have this at 1, it's gonna set the first, the 1 first, or not the first, but the bit with index 1. And basically this tells the Windows API which core shall run this thread. So I'm just going to leave it at 0 and start this application again, and you will see that CPU 0 will go at 100% peak while the thread is being executed. and you can see that the just thread 0 is gonna run this. Can start this a few more times. So let's start this again, and you will see that it will directly go to thread 0 again, and we can start this as many times as we want, as it will always go to this thread 0 because we have set the affinity to just thread 0. We could also like combine this with multiple threads, so you can take a logical operations and not the logical compare, so actually bitwise operation here, and you could like add another one in here. So I could like add thread index +1 in here, and this would now mean that it runs on either core 1 or core 2. It would probably start at, yeah, now you can see it's starting at core 2, and I'm gonna rerun this until we see that it goes to thread 1 again, or core 1 again, virtual core 1 again. It's going to 2 again. I don't know why it could actually be that core 1 is a bit reserved by Windows, and it does like to do its scheduling, but actually you can see like Windows is doing its scheduling like on the cores that are further away. You can see like the first cores are all like idle, and Windows and background processing is all done on the cores that are having higher numbers. This is most of the time because people say, okay, I have an application that runs on 8 threads. Well, let's start at core 1 to 8, and Windows says, screw it, if I'm gonna occupy the first threads, like the dumb programmer is gonna use them. And Windows is also using them, so Windows is just scheduling them at the back, so that yeah, the application engineers are probably like a bit more concerned. Why are you always running on core 1, CPU 1 now? That's a bit bad. It could be like Windows scheduling, that Windows is actually prioritizing like this core CPU C1. Looks like Windows is like prioritizing the CPU 1 here. I probably cannot force it. Okay, I can force it by just removing this again, but basically, yeah. I can like directly specify which core I want to go on. Let's go on 31 here. Let's start here, and we're gonna see that 31 is gonna pick up our work. Yeah, there you see 31 back on 100% processing because of the while loop. You can see like CPU 31 is now performing all of our work here. So basically Affinity, nice thing. Alright, let's remove this pointless work because it is like pointless, and let's continue on with some more stuff that we want to do. So alright, let's actually show you something how you can input and output data from the thread. So basically these are input variables and this is output. So basically what I want to have is I want to have an uchar, or actually a byte, blob. And basically what I'm gonna do in this blob, I'm actually saying blob is actually arguments, blob args, blob is equal to arguments thread ID modulo 255. So just pointless converting, doing dumb calcs, so we're doing some dumb calculations. And what I could do, like here on this exit code, I could say finished with that, std deck, std handle, the blob is, then say args blob done. And now you can kind of like see the thread ID 31180. 31180, let's do calculator, let's go to programmer mode, 12280, modulo 255 is 40, and I've screwed up the thread ID. 31180, I'm always like, have no good mind. 31180 modulo 255 is our 17, and you can see that continuing this that basically this blob is correctly calculated. So just some basically some return value from the thread using our arguments. So basically, as soon as the thread finished that, you know that all of the output variables are now valid, And yeah, everything is going to plan. Now let's actually do this a bit differently. Let's actually do this dumb calculations after the message box, so you can actually see what happens if you abort your thread. So let's just put this down there and just wait the idle time. Okay, now I need to wait 10 seconds again. This is a bit unfortunate, but yeah, it's not gonna be that big of an issue. So let's just wait a bit of a time. And you see that the message box has been aborted, and now you can see that the blob has the value 204. And let's take a look at the thread ID. 33416. 33416 modulo 255. It would be 11. But we got 204. This is just because this calculation was never been done. So you need to take the awareness that if you abort your thread, that the output variables may not be valid. So it would be to properly initialize this blob to 0 previously, or to an invalid value, or kind of like something else, and then you would kind of like at least get 0, where you then know, okay, a blob of 0 means, yeah, okay, actually a blob of 0 could be valid because you're doing modulo operations. But yeah, alright, so press OK. Everything is going to plan. Alright, so now let's do a breakpoint here, and I'm gonna show you something. You can actually see that this thread here has a number, and this multi-thread tutorial X thread main. Now imagining you are having a job system on your game engine, for example, and this is called job main, for example. And you have like 100 threads all running at your job main. It's very hard to see what thread you are currently on, because like this is very cryptic. You cannot see what's going on here. Of course, you could kind of like remember that thread IDs, but it is not quite quite nice. And there's a thing called thread naming. I don't know the functions in my mind. I don't have them, so let's just Google them. WinAPI set thread name, and this is actually quite easy. Let's go Stack Overflow. Okay, this is like bad. Thread description is actually the function. Yeah. So I'm gonna set a thread description here. I'm gonna do this directly after creating the thread. So we're gonna set thread name. So we're gonna set the thread description. I'm gonna input my age thread here, and I can, is it a white string? Yes, it's a white string, and I just say this is the message box thread. Just very easily, just like that. And now, in case I start this, and I'm gonna reach this breakpoint, you're gonna see that up here we have now a nice description message box thread. This is very nice because this just gives us an insight on which thread we are currently on. And in case you have a job system, you would kind of like have called this like job thread #0, #1, and you can easily like see on which thread you are. So in case you're hitting the next breakpoint, you can easily see, oh, now I'm on job thread that, or you're actually tracking some data, and you can see like, oh, thread that has done this work. And you could actually try out, I think you can get the thread description as well. So let's try this out if this is actually possible. So, how was the function called? Get thread description, which needs a, okay, it's actually like that. So I actually need to output this here. So we're gonna build the message here, and we're gonna get thread description. So what was the things here? PV string. I'm not. That's actually. I wanna take a look at this function before I'm gonna use this. I hate it. A Unicode string that contains the description. Pointer to white string. Let's see. Can I? Okay, I need to use this local free. Okay. Alright. This is good. Okay, I was just a bit confused how this is gonna be used. Okay, I need to use the local free. Good, okay. So I'm gonna have a white string here. So p white string. Actually, this should just be a... Yeah, let's just do a vchar pointer. Thread name, which will be equal to that for... Yeah... I mean, I know that it's bad, but I just want to have this like that. Alright. Yeah. So, let's actually get this. We're gonna need to get thread handle. Get current thread, which shall give us the handle of the current thread. And we need the thread name here, pointer to that, and this will just give us the name of the thread. And I can just input this into the white string here, and then we're gonna close this brackets here as well. And we can also, maybe let's just stop the execution here at some point. And down here, what I'm gonna do is, after this is like being used, so actually after this was in the message box, you can actually check free the name, that the name shall be only freed if the length of the string is bigger than 1 or bigger than 0. We see as lang, give us the length of a white string, we get inputting our thread name, and if this is bigger than 0, or we could actually just check for the length, just like that, then we're gonna use local free for our thread name, which will probably just free up our thread resources. So this should be good. All right, now let's try this out. If this is working. Yeah, so you can now see thread 28032 message box thread. Hello, I'm a message from the thread. So you can like easily track down your threads and your names. You can easily like get this description and retrieve it back again, and this is quite nice to make your thread run on a higher priority. So you can set a thread's priority. Set thread priority. It's very easy. So you have your H thread, and you need to specify a priority. It is like there are several priorities available. If you take a look at the documentation, you can see that we have several priorities. Background, but it's like, yeah. Actually, the interesting priorities are these priorities. You have like the normal priority. You have below normal, so it's like not as prior as you may want to have it. You have lowest priority, and you have idle. Idle basically means that your current thread is idling. You can, yeah, basically, if it has no work to do, you can set its priority to idle, and Windows will no longer schedule that thread that often. So it's kind of like not that high in scheduling, and as soon as you kind of like have some work and you may want to schedule this on the thread, you basically increase the thread's priority back to like normal, for example, and Windows will again start on scheduling this thread more often. Of course, you also have high priorities. You have above normal and high, and you have time critical. This is something you shall be really concerned of using. You can actually crash your whole system. There is a function where you can retrieve the number of cores your system have. Get system... I think it's get system info as far as I know, which is the system info struct, system info sys, and there should be yeah, this double word number of processors. And basically what you can do, you can use this this value here after getting the system properties, and you can write a loop, a for loop over this number of processors, and you can create the number of threads for. So you can create the number of threads as processors, and you can set this affinity to the current index of the thread with the affinity mask. Basically, you can schedule as many threads, as many cores as you have, and bind each thread to one single core so that each thread has its dedicated core. Then you can set this priority to real time, and you can also like set the whole application's priority. So set process priority. Okay, it's not priority, set process. Where was that? Wasn't that priority? Not quite sure. yeah, I need to take a look at this, but you can actually also like set your whole application's priority. And if you kind of like set your application's priority to global real time and all your threads priority to the highest priority, your complete system will just lock up. No blue screen, nothing, just locking up. Of course, you kind of like need this while loop in your thread, of course, in your thread main, but you can completely lock up your system with that. Yeah, actually I may do some serious, actually it's a bit hard to make some videos how you code malware, because you need an external capture card to capture like systems crashing, but I may do some informative series on how to troll your Windows users by using WinAPI, or I may not do this. I'm not quite sure of that. It's a bit, yeah, maybe I install some Windows in a virtual machine to show you how you can do something like this, but I'm not quite sure if I want to do this because people would abuse this. Alright, so actually like this is the important page here, this scheduling priorities, because this is how Windows is scheduling. Ah yeah, okay, these were these classes, so these are the classes the threads are bound to. So this is actually set priority class is the function for an application. Set priority class, which takes a process, get process, get current process, yes, get current process, gets your current process handler, and then you can add this priority class. In the case you set this to, like, you have idle, below normal, normal, above normal, high, and you have this real-time priority class. And if you input real-time priority here, and then you set your thread priority to time critical, then you kind of like have the most high priority that a thread can have. You shouldn't do this. You can like see the actual priority. So you can see that if you are on idle, the priorities go from 1 to 15. If you have like normal, they are also going from 1 to 15. But okay, yes, of course, because 1 and 15 is always like, time critical is always 15 and idle is always 1. But you kind of like are interested in these middle ones. Actually, like process isn't required, as you can see. So 4, 5, 6, 7, 8, and here you have 2, 3, 4, 5, 6, and you kind of like have always this base priority that is always higher. So if you're normal, your range is 6 to 10 with your normal priorities, and if you're like high, you're 11 to 15. But real-time priority actually has a bit more, so you need to have real-time and time critical to earn the highest priority that is available. So real-time is always above all other priority classes. So it's a bit, yeah, different on Windows, but you can do so many stuff on Windows with threads and processes. You can also have fibers. I may also like do some videos about fibers in the future at some point, maybe. Fibers are basically user mode threads. So basically you can implement your own thread scheduling by using fibers, which is quite nice actually. Yeah. But you need to take attention because you can actually have some issues. Fibers are not as easy to implement as you may think. They have like their own context and they are quite nice, but they are, you need to take them with a bit of caution, fibers. Alright, but let's actually get rid of the priority stuff because we are not wanna do that in this video. Alright, don't need that anymore. There we go. Alright, so this is everything I want to tell you about WinAPI threads. I mean, like, well, we don't have that many code, we doesn't have done some synchronization, we haven't done some work. We just have discussed how WinAPI threads are working and how you can archive nice things with them. I hope you enjoyed. I think it's very important in case you want to actually are in this kind of like graphics standpoint, because I would not advise you to write your graphics engine with STD threads. No, because WinAPI threads. You write WinAPI threads. There is an equivalent on Linux, pthread, which is POSIX threads. You're basically, if you're writing a complex system, you want to actually go for native libraries. If you're writing a complex system like a renderer, or basically your renderer wouldn't need this because your renderer is basically just an abstraction, or basically no, your hardware abstraction would not use this, but basically your renderer and your game engine may use threads. Basically, if you have a game engine, you probably have a job system and some good arrangement and user and own program and scheduling. So you want to basically use this. So basically, there is a talk on YouTube. I mean, can I quickly find this talk? So I needed to take my physical book reference I had, and basically it is not on YouTube, it is on the GDC vault, parallelizing the Naughty Dog engine using fibers, which is basically a 1-hour talk which is going into the detail of how to use threads and fibers to create a job system. So yeah, if you are interested in some advanced topics there, you can watch this for free. You don't need to log in. It's actually quite nice because it's not members only. You can just yeah, look at this. I already like The Last of Us was made with that system on PlayStation. And they actually made it run on 60 FPS by using a job system, which made things a bit faster. And I would really recommend, in case you want to actually get some information there, another hour of video. So in case you want, I will have this link in the so I'm gonna have this link in the video description. So yeah, thank you for watching. We're gonna see us in the next video. I'm not gonna quite sure what this is gonna be. I still need to do some more work before I can continue my real-time rendering, but this is gonna be continued at some point. I also have some other commercial projects I need to finish now, some projects at work, and I'm quite a bit on demanded currently on like programming other than YouTube, which is a bit bad because you're not gonna get such high frequency of videos. But yeah, you're gonna get the videos at some point, even though it may be some different videos or not many videos at the current point of time. So yeah, thank you for watching. Gonna see us in the next video. Make sure to like and subscribe. And what do your people say? Activate the channel and like the bell. Yeah, probably. Thank you for watching. Have a nice day. Bye.